As we close out this module, I want to give you a slightly different definition, a more expanded definition for lattice energy than the author gave you. Lattice energy is a form of potential energy, and he gave you the part that says the energy required to break apart an ionic solid, but the expanded definition that I'm adding is and convert its component atoms into gaseous ions. If you look at the example he gave you in the book where he is using the Born-Haber process and Hess's law to calculate the lattice energy for sodium chloride, you should notice that he actually, through that process, he is taking the sodium ions and the chloride ions, and he's actually converting them into gases. And so that's why I've added this piece to the definition, because that is actually the definition that you're normally going to see. He has shortened it a little bit, so I wanted you to be aware of that. Now, we have talked very briefly already that bonds are stronger when you've got higher charges and smaller atomic radii, and that's also going to be true for lattice energy. Your lattice energy is going to be greater as your ions get smaller and your charges get higher. So let's do a sample problem here. If I have these four compounds, which one of them has the greatest lattice energy? Well, you'll see that all of them are metals that are bonded to chlorine. And so they're all ionic solids because it's all metals combined with nonmetals. If I look specifically at charge, that's probably the easiest one to see. Sodium and potassium both have a +1 charge. Calcium has a +2. Aluminum has a +3. The chloride ion is a -1 in all of them, so that's a common factor there. So aluminum has a +3 charge. So from the charge aspect, that would tell us that it is the one that has the greatest lattice energy. I can also look at it from the concept of atomic radius. You should remember from your first year course that atomic radius increases as I go from right to left across the periodic table and as I go from top to bottom down the periodic table. Now, it's probably, again, just as a form of review, it's probably pretty intuitive that as you go down the periodic table, the atoms are going to get bigger. That makes more sense because every row I go down, I've added yet another energy level and I've added more atomic orbitals. So that obviously is going to make the radius larger. But how about from right to left? How does that work? Well, I'm only going to have a certain number of electrons, or rather a certain size of the electron orbitals. And so as I go across, if I look at the first couple of rows, for example, I'm going to have an s orbital and a p orbital, and they're going to be of a similar size. But as I go further and further to the right, what am I adding? I'm adding electrons, but I'm also adding protons. And so the protons that I add to the nucleus are going to have a stronger pull, and they're going to attract those electrons that are orbiting them in. And so that's actually going to shrink down the size. Okay, so the atomic radius is actually going to increase as I go from right to left, because the additional protons over here are just going to draw that electron cloud in tighter and tighter. Okay, so if I look at where these are located, aluminum's over here, and then I've got, if you look at the periodic table, in the same row as aluminum, you've got sodium, and then under sodium, you've got calcium, and you've got potassium. And so that's a definite, as I'm going from right to left, the aluminum's going to be bigger than the sodium, and then the sodium is also going to be, the aluminum's going to be smaller than the sodium. Sodium's going to be smaller than both the calcium and the potassium because they have an additional atomic orbital. So for both reasons, this aluminum chloride is going to be the solid that has the greatest lattice energy. Okay, and that completes module 4.